Hey guys, it's me, Miss Wesley, back to talk a bit more about polar coordinates and plotting polar points, but not just polar points like you see at the top of page 5 of the polar packet. I want to graph full out polar equations with you today. Here's a little joke to start things off. How would a bunch of astronomers organize a party? Well, it's simple. They would plan it. It'd be easy, and I bet yours will be neater than mine, to sketch out the set of points that are all 4 units away from the pole or 4 units away from the origin. This is going to be a circle of radius 4, like it looks like here. Converting to rectangular form, we know it's easier if you'd square both sides. If r is 4, r squared becomes 16. And then you've got x squared plus y squared equals 16. So there's your rectangular form. How about theta equals 45 degrees? Okay, so what shape is this going to be? We've seen equations like this before. You need all the points where their central angle will be 45 degrees. I'm going to plot a line with the 45-degree central angle going up through quadrant 1, and can you extend it down through quadrant 3? There's your line. I'm wondering if you could guess off the bat that its rectangular equation is going to be y equals x. And we know there's a definite reason for that, and that reason is that we know that tangent of theta always equals y over x if we're trying to convert to rectangular form, and theta here is 45 degrees. So tangent of 45 degrees equals y over x. Tangent of 45 degrees is 1, and that equals y over x, which leads you to this rectangular form. All right, now for the fun part, the actual graphing. Let's look at the top of page 6, number 7, where we're asked to graph r equals cosine of theta. Before you get started, take a look at the set of axes that you have here and give yourself a good reminder of where the 4 quadrant lines fall. So you have 0, you've got pi over 2, you've got pi, and then down at the bottom, 3 pi over 2. And for fun, we could put in the multiples of pi over 4. A quadrant 1 multiple, you've got 3 pi over 4, you've got 5 pi over 4, and then 7 pi over 4. Okay, that'll just get our bearings going. Now it's time to just take the cosine of each one of these values that you see listed in this table, right? I specifically chose angles where we would know some exact values. Cosine of 0 is first up. Cosine of 0 equals 1. We're not going to get an r for this one above 1 or below -1. So I'm going to label this as 1. We're going to go 2 circles out to come to 1 unit, and then 2 more circles out to get to 2 units, and 0 is right on the pole. So if I'm plotting these points here, I'll switch to blue, and I'm plotting a point at 0, 1, which will be right along the x-axis. All right, 1 down, a bunch to go. What is the cosine of pi over 6? Square root of 3 over 2 is your exact value. Because we're just eyeballing where these points are going to fall as we graph by hand, why don't we round it to the nearest tenth? So it's 0.866. We'll round it to about 0.9. Pi over 6 would be 2 lines up from the polar axis, and we're just coming to 0.9, so we're curving inward like that. Okay, cosine of pi over 4, square root of 2 over 2 is about 0.707, right? Really just 0.7 would be fine, and that's going to be about here as we curve in. How about cosine of pi over 3? We know that as a half. Pi over 3 is on this line. And we'll come out a half, which is 1 ring out, the way that we have this labeled. And pi over 2, what's the cosine of pi over 2? We know that's 0, and we have a dot right on the pole, right on the origin. So congrats, right? We're done with our first quadrant worth of points. Now we got to go down the rest of the table. 2 pi over 3, that falls here. 2 pi over 3 is going to be on this line in quadrant 2, but I don't think the point's going to be in quadrant 2 because here the cosine is going to be negative. The cosine of 2 pi over 3 is going to be negative a half. What that means is we got to flip-flop down into quadrant 4 at 5 pi over 3. We're going to come a half a unit out this way, and we've got our quadrant 4 point labeled there. So that one's taken care of. How about 3 pi over 4? Cosine of 3 pi over 4 is negative square root of 2 over 2, which is to the nearest tenth would be enough, negative 0.7. So 3 pi over 4 is up here. We want to flip-flop down to the line that's labeled 7 pi over 4 and come out about 0.7 of the way. Okay, curving our way back up. I see definitely some symmetry above and below the x-axis. How about 5 pi over 6? Cosine of 5 pi over 6 should be this exact value, which rounded would be negative 0.9. So 5 pi over 6 is here. A negative radius causes me to flip-flop over to 11 pi over 6, and we're coming out 0.9. And pun intended, I've come full circle back around to 1. Speaking of which, what happens when I get to plug in cosine of pi? Cosine of pi actually is -1. Do I have that point already? Well, we do. Here's pi. Negative means flip-flop over to the other side. And it looks like I actually already have that point. I've overlapped a point that I already knew about. Will the same thing happen as you go down this entire list? Cosine of 7 pi over 6 is negative square root of 3 over 2. Do we have that already? Negative 0.9. So 7 pi over 6 is here. Flip yourself over to pi over 6. We actually already have that point. And just to give it away, we could continue with these values, but this one is just going to be a case of repeats. We know that trigonometric values are always going to be cyclical. We're going to get some of the same ones down at the bottom of the page. It'll just give itself another rotation around that circle. And this is a circle. Now's the fun part. We get to connect the dots. So can you, in your nice smoothest curve, play a little game of connect the dots that you just plotted? Mine, I always think mine kind of looks like a seashell. It just reminds me of a seashell on its side. This is a circle. And a circle happens when you're given any polar equation of the form, just to give you a sense of this, of the form a cosine of theta or a sine of theta would have also been a circle. There's some things we could have guessed about this original graph just by looking at the equation. Your original coefficient out in front of the cosine of theta, your a value is going to equal 1. And that's the reason this circle doesn't come out beyond the 0.1. If I had put a 2 out front, you'd have a circle of double the size. And this circle is off center from the origin. I'll just put an exclamation point there because of the way that it's given. We know if we had a circle like r equals 4, r equals 7, that one would be centered right on the origin. Lastly, in this space that we have over to the right-hand side, I think this is a good opportunity to practice with converting. So I want to see if we can convert this original polar equation into rectangular form just to convince ourselves that this really should be a circle and because it's great practice. Well, how are you going to do it? There's no one magic right way, but we know that we could rewrite cosine of theta by its definition. Cosine of theta by definition is always going to equal x over r. We're getting there. We're trying to make this rectangular. It's nice to have the x there. We've got to get rid of these r's. So why don't we multiply an r to the other side? And we get the equation r squared equals x. Now I like this. I know for r squared, I can plug in x squared plus y squared using my conversion formulas. And this now looks like an off-centered circle. Minus x equals 0. So here's one way to write it in general form. If somebody needed it in standard form, we could complete the square once to be able to get that. And that is looking pretty good. All right, I'm excited to see what this next one looks like. Number 8, it says r equals 2 plus 2 cosine of theta. Let's give it a try. So start by labeling the diagram up a tad. Let's at least remind ourselves of the 4 quadrantal angles. So 0, pi over 2, we've got pi, and then 3 pi over 2. As long as we want to label this as we go. So start by plugging in a 0. 2 plus 2 times the cosine of 0. Think of the cosine of 0. We know that that's going to be 1. So 2 plus 2 times 1 gives me 4. That's why it's good that we had just enough room to come out that far on the picture. Let's put this on the picture. We'll go zeros here. This is 1 unit, 2 units, 3 units, and then here's 4 units with a dot right on the outside of that. All right, next up, pi over 6. So this is 2 plus 2 times square root of 3 over 2. And that's really exact value, 2 plus the square root of 3. I would just have my calculator handy to be able to round that, so it'll be easy to graph. And you get to the nearest tenth, you're going to get 3.7. So where are we going here? Pi over 6 is 2 lines up. We're coming out, not quite to 4, we're coming out 3.7 and curving in to put a dot there. Next up, pi over 4. This is 2 plus 2 times the square root of 2 over 2. So calculator-wise, 2 plus the square root of 2 this time gives me about 3.4. So on the picture, pi over 4 is at 3.4. So I'm curving around a little bit further in. Pi over 3, 2 plus 2 times a half, and this is really just 2 plus 1 gives me exactly 3. So pi over 3 is here. we're down to 3 units. This one's kind of starting like a bigger scale version of the last one where it's curving back and around. I wonder what these two 2's really do to it. So how about pi over 2? 2 plus 2 times the cosine of pi over 2, which is just 0. So you have 2 plus 0 gives you 2 for this value. So pi over 2, you're down to the second ring. All right, we're out of quadrant 1, into quadrant 2. 2 plus 2 times the cosine of 2 pi over 3. So this is going to come out to be 2 minus 2 times a half. So minus 1 equals 1. So at 2 pi over 3, we're down to 1 unit out. We've got a dot there. 3 pi over 4, exact value. Feel free to pause the video and come up with your exact values. For this one, we're going to have to fill out the entire rest of the table. But if I'm going a little bit too quickly with the values, feel free to pause and fill them in yourself and then kind of check with me. 2 minus the square root of 2 is going to be about 0.6. So here we're curving in. We've got 3 pi over 4, which is the line here. You're at 0.6, so we're getting really close in towards that pole. How about 5 pi over 6? Your exact value would be 2 minus the square root of 3. And then your rounded value would be about 0.3. We're getting even closer. So 5 pi over 6 is here at 0.3. You've curved in. Okay, what about pi? 2 plus 2 times the cosine of pi is going to be 2 plus 2 times negative 1, right? So plus negative 2 gives you 0. So you're right on the pole. That is half of the story, and we've only filled out half of the table. Let's look at 7 pi over 6. So 7 pi over 6 is 2 minus the square root of 3, which is about 0.3 again. So 7 pi over 6, we get a little bit of symmetry here. And you're at 0.3 on this line, very close in toward the pole. 5 pi over 4 is a repeat value too, 2 minus the square root of 2. So you're at about 0.6. So 5 pi over 4, you're at 0.6. 4 pi over 3, you're going to get 2 minus 1 gives you 1. So 4 pi over 3 gives you 1. And then we skip a line to go to 3 pi over 2. 3 pi over 2 should give you 2 minus 0 gives you 2. So 3 pi over 2, you're down 2 units. The rest of the points are going to be exactly symmetric with respect to that line, the polar axis. 5 pi over 3 is going to give you exactly 3. 7 pi over 4 is 2 plus the square root of 2, which is around 3.4. We've seen that value. 2 plus the square root of 3, which is around 3.7, and your last value is a repeat. It's at 4. So watch these points overlap. Where was I at? 5 pi over 3, I believe, is here. So we'll go 5 pi over 3. We said is at 3, so we're here at the third ring. 7 pi over 4 is at 3.4. 11 pi over 6 is at 3.7, and then 4 is a point that we've already had. Now to connect the dots, see what you can do. Let's curve this thing around, and I wonder if this looks romantic at all. Actually, let me zoom, see if I can zoom this back in so it's a smaller set of points for me to curve around to. Does this look at all romantic? It's supposed to be a heart-shaped figure. It's supposed to not look like a rear end. It's supposed to look like a heart. Its name even sounds sort of like a heart. This graph is called a cardioid. And a cardioid is a special type of another graph called a limacon. L-I-M-A, and then the letter they use it in French, a little C with a tail on the bottom, limacon. Kind of sounds like lima, or looks like lima bean to me. But a cardioid is going to be a heart-shaped graph, special type of limacon, where you're given an equation of this form. Either R equals A plus or minus B sine of theta, or R equals A plus or minus B cosine of theta. And you'll get that heart shape as long as, to get a cardioid, right, A over B must equal 1. As long as the ratio of A to B is 1 or A is the same as B, that's when you'll get a heart shape. Quick test for symmetry and polar coordinates. The graph of anything in terms of sign is going to be symmetric with respect to. Those are my little letter abbreviations. Symmetric with respect to, we'll say the line, theta equals pi over 2. So if we were to graph this in terms of sine, it would be symmetric with respect to a vertical axis of symmetry. And since we graphed something that was in terms of cosine, we're symmetric with respect to the horizontal polar axis, the polar axis, which has the equation theta equals 0.